This is the first of a series of videos looking at methods for solving first and second order differential equations and some applications of these differential equations. So to begin with, let's consider the differentiation of the expression y cos 5x with respect to x. In order to differentiate that, we need to use the product rule because we've got y times cos 5x to differentiate. And differentiating, we'll obtain dy by dx times by cos 5x plus y times the derivative of cos 5x, which gives me dy by dx times cos 5x plus y times minus 5 sin 5x. In other words, we've got dy by dx cos 5x minus 5y sin 5x. Or equally well, we can write that as cos 5x dy by dx minus 5y sin 5x. Now have a look at this expression. We've got x cubed times by dy by dx plus 3x squared y. Now if we think of that as being dy by dx times by x cubed plus y times by 3x squared, we might be able to see that this is actually the result of using the product rule on y times by x cubed. So we can say that x cubed dy by dx plus 3x squared y is the same thing as the derivative with respect to x of y x cubed. And we can say that the expression x cubed dy by dx plus 3x squared y is the result of differentiating y x cubed with respect to x. And we say that x cubed dy by dx plus 3x squared y is an exact derivative. It is the result of differentiating y x cubed with respect to x. In a similar way, if we look at the expression cos 5x dy by dx minus 5y sin 5x, that is also an exact derivative because we have seen at the top of the page that it is the derivative with respect to x of y times by cos 5x. Now at this stage, what I'd like you to try and do is pause the video and see whether you can fill in the gaps in this particular table. When you've finished that, you can unpause the video, start the video again, and we'll continue and we'll try and see how we are going to make use of exact derivatives to help us solve a variety of differential equations. Okay, I hope you've managed to get this exercise done. What we want to do now is we want to consider the differential equation x squared dy by dx plus 2xy equals e to the 2x. Now if we look carefully at the left-hand side of this expression, x squared dy by dx plus 2xy is an exact derivative. It's the exact derivative of y times by x squared. So the differential equation can be rewritten as d by dx of y x squared is equal to e to the 2x. Now we can we can integrate each side of this equation. So if we integrate a differentiation, we just get back to what we originally had, which is y times x squared on the left-hand side, and on the right-hand side, integrating e to the 2x, we get a half e to the 2x plus, and this is important, a constant of integration. So we've got y times x squared is equal to half e to the 2x plus c. In other words, we have got y is 1 over 2 x squared times by e to the 2x plus a constant divided by x squared. The solution, y equals 1 over 2x squared e to the 2x plus c over x squared, is called the general solution of the differential equation. Now this example is an example in which the left-hand side of the equation was an exact derivative. And when this is the case, we say that we've got an exact differential equation. And if that is the case, solving the differential equation basically relies on us being able to integrate the right-hand side of the equation. So, what we're going to try and do now is we're going to consider the differential equation dy by dx plus p of x times y equals q of x. And what we're going to try and find is a function, if you like a magic function, which we'll call f of x, which will turn the left-hand side into an exact differential equation if we multiply the equation through by f of x. So, how do we find this magic function f of x? Well, what we want is f of x times by dy by dx plus f of x times p of x y to equal f of x times q of x. That's just the effect of multiplying through by f of x. But crucially, we want the left-hand side to be an exact derivative. Now, using the product rule, we know that if we try and differentiate y times f of x with respect to x, we will obtain f of x times by dy by dx plus f dash x times y. Now, this will be exactly the same as the left-hand side of equation 1 if we have f dash x equals f of x times by p of x. So what we want is we want f of x times by p of x to equal f dash x. If we rearrange that, we've got f dash x divided by f of x has got to equal p of x. And if we integrate each side with respect to x, we've now got the integral of f dash x over f of x with respect to x has got to equal the integral of p with respect to x. Now you'll have met integrals of the form f dash x over f of x several times before in your studies, and we know that the integral of f dash over f is simply the logarithm of f. So we've got the logarithm of f of x must equal the integral of p of x. In other words, we have got f of x, our magic function that we're trying to use, must be e to the integral of p of x. So, what we've seen is that the differential equation dy by dx plus p of x times y equals q of x can be turned into an exact differential equation if we multiply each side of the equation by f of x, where f of x is e to the integral of p of x, and then the left-hand side of the equation becomes the exact derivative of f of x times y. So let's try and see this in practice. So we're going to try and find the general solution of the differential equation dy by dx plus 2y equals 8x, and find the particular solution of this differential equation that passes through the point 0, 5. Now we've got dy by dx plus 2y equals 8x, and we're comparing that with an equation of the form dy by dx plus p of x times y equals q of x. So we've got p of x is just equal to 2, and q of x is equal to 8x. The integrating factor in this case is e to the integral of p of x dx. So that is e to the integral of 2 dx. Now the integral of 2 with respect to x is just 2x. Don't need to worry about the constants at the moment, and perhaps your teacher might explain why later on. So we've got the integrating factor for this differential equation is e to the 2x. So we must multiply the original equation through by e to the 2x to obtain e to the 2x dy by dx plus 2e to the 2x times y equals 8x e to the 2x. The left-hand side is now the exact derivative of e to the 2x times by y. So we can rewrite the equation as d by dx of e to the 2x times y equals 8x e to the 2x. So that's where we've got to at the moment. So we now need to integrate each side with our new differential equation with respect to x. So the left-hand side just becomes e to the 2x times y equals the integral of 8x e to the 2x dx. Now the integral of 8x e to the 2x dx is going to require integration by parts, and if you go through your integration by parts, you'll obtain the fact that the integral of 8x e to the 2x is 4x e to the 2x minus 2e to the 2x, and at this stage we do need to remember the integration constant plus c. So we've now got e to the 2x times y equals 4x e to the 2x minus 2e to the 2x plus c. Dividing each side by e to the 2x gives me y equals 4x minus 2 plus c divided by e to the 2x, but c divided by e to the 2x is the same thing as c times e to the minus 2x. And that is our general solution of the equation. And finally, we want the solution of the equation that passes through the point 0, 5. So when x is 0, y has got to equal 5. So we've got 5 equals 4 times 0, which is 0. Take away 2, add c. So c must be equal to 7. So the solution that passes through the point 0, 5 is y equals 4x minus 2 plus 7e to the minus 2x. We'll now move on to a second example. Use an integrating factor method to find the general solution of the differential equation x dy by dx minus 4y equals x to the power 5 e to the minus 2x. Now it's important here to remember that to use the integrating factor method, the original equation must be in the form dy by dx plus p of x times y equals qx. Now, if we're going to do that, we're going to need to just do a little bit of rearrangement. So we need to divide through by x first of all. So we get dy by dx plus minus 4 over x times y equals x to the 4 e to the minus 2x. And that is now in the right form to be using the integrating factor method. So we must have the left-hand side in the form dy by dx plus a function of x, p of x, times by y. And the right-hand side must simply be a function of x. So, the integrating factor is going to be e to the integral of p. So in this case, that is e to the integral of minus 4 over x. Minus 4 over x integrates to give me minus 4 ln x. Which is the same thing as e to the logarithm of ex to the minus 4. And if I take a number, find its logarithm, and then raise the answer to the power e, I just get back to the original number that I started with. So e to the logarithm, natural logarithm of x to the minus 4 is just x to the minus 4. So my integrating factor is x to the minus 4. So I am going to multiply my equation star by the integrating factor to obtain x to the minus 4 dy by dx. Then I've got minus 4 over x times by x to the minus 4, so that gives me minus 4 x to the minus 5 equals, now the right hand side is x to the 4 e to the minus 2x times by x to the minus 4, so that just gives me the e to the minus 2x. The left-hand side of the differential equation is an exact derivative of x to the minus 4 times by y. So we've got the d by dx of x to the minus 4 times by y equals e to the minus 2x. Integrating each side is going to give me x to the minus 4 times by y is equal to the integral of e to the minus 2x with respect to x. In other words, x to the minus 4 times by y must be equal to minus a half e to the minus 2x plus a constant. Do remember the constant at this stage. And if we multiply through by x to the 4, we are going to obtain y equals minus a half x to the power 4 e to the minus 2x plus c times x to the 4. And that's the general solution of our original equation. Okay, now to finish off, there's 4 equations here, each of which can be solved using the integrating factor method. Stop the video, have a go at these 4 questions, and then perhaps you'll be able to discuss the solutions with your teacher when you review this work. And that concludes our first video looking at the solution and applications of differential equations.